Okay, so what section 6.6 is about is how calculus, how integration can be applied to applications in physics and engineering. Okay, and you know, you don't have to be like you know, there's some fun basic physics concepts in here that I'm sure most of you have seen either in Calculus 1 or maybe even in high school. Let me just kind of review a few things with you here. Okay. So one thing is called, and I have some things highlighted here, work. How many have heard of the concept of work in maybe in a class, a science class? Okay, Jacob and Abidar, Maria, Audrey. So quite a few, Audrey, and quite a few of you. So, okay, what is work? Well, work means the total amount of effort required to perform a task. That's the everyday use. But in physics, it has an idea in terms of force. So you can think of a force as describing a push or a pull on an object. For example, a horizontal push of a book across a table, or the downward pull of Earth's gravity on a ball. If an object moves along a straight line with a position function, then the force on the object is defined by Newton's second law of motion like this. Let me bring it down here. This is Newton's second law of motion. So what does this mean here in the box? What is Newton's second law of motion? Force equals
mass times acceleration.
Mass times acceleration. That's right, Maria. So remember well, in terms of let me just go to the whiteboard real quick. So this is position, right? How many recall position from Calculus 1? Position, a position function. Okay, Renald remembers it. And if you compute s prime of t, which is equal to ds dt, what is the derivative of position?
Velocity.
That's right, velocity. Now, if you take the second derivative of position, which is the same as the derivative with respect to t of ds dt, which can, you know, we have it in Leibniz notation. This is written as d squared s dt squared. What is the second derivative of position?
Accelerate.
Acceleration. Okay, and Newton's law, second law of motion, says force equals mass times acceleration. That's Newton's second law. So, in the book, then, if we go back to the book, there you go. Force equals mass times acceleration. Now, we do have to worry about units, right? We have to worry about units. So, I always like to kind of highlight things. So, in the SI metric system, mass is measured in kilograms, displacement in meters, time in seconds, and force in newtons. Okay, so how many have seen newtons maybe in another class as a measure of force? Okay, Jacob has. And well, 1 Newton, the force of 1 Newton, and Samuel has, excellent. The force of 1 Newton acting on a mass of 1 kilograms produces an acceleration of 1 meter per second squared. Okay, that's just so Newton is defined as kilogram times meters divided by seconds squared. That's the force in newtons. Now, in the US customary system, the unit of force is the pound. Okay, so these units are going to be important to recognize in your when you do your homework. And here's the definition of work. Work equals force times distance. Okay, how many have seen that definition before? Okay, Marcus has, and oh wow, a lot of you. Tal, Gloria, Jacob, Michelle. All right, so work equals force times distance. So, you know, just kind of reviewing a few things here. Reviewing a few things. I want you to be comfortable. So force, let me highlight this. So if force is measured in newtons and distance in meters, then the unit for work is the Newton meter, which is called the joule. Okay, work can be in joules. However, if force is measured in pounds and distance in feet, then the unit for work is in foot-pounds. Okay, so for instance, so you have for units of work, you have joules and you have foot-pounds. And your homework problems will give you, you'll do different kinds, you know. So for instance, suppose you lift a 1.2 kilogram book off the floor to put it on a desk that's 0.7 meters high. The force you exert is equal to the opposite of that exerted by gravity, right? Because to lift the book up, to get it on the desk, you have to apply a force opposite to what gravity is doing. So gravity, what's that 9.8 there? In force equals mass times g. G is gravity, and the acceleration is the gravity. Okay, acceleration due to gravity is 9.8 meters per second squared. So in this little example, the force would be 1.28, okay, 1.82 kilograms times 9.8 meters per second squared. And that'll give you 11.76 newtons. Okay, is that, so far are we good? Okay, so that's the force. Good, Jacob. Thank you. And now the work done, the work would be equal to the force times the distance, which is the 11.76 newtons times the 0.7 meters. And that's Newton meters, that's 8.2 joules. Okay, and by the way, some of the problems in the homework, they'll give you like, instead of 0.7 meters, they might give you, you know, 0.70 centimeters, right? That'll happen. So whenever you have centimeters, you have to convert it to meters. Just keep that in mind. Whenever you have centimeters, you have to convert it to meters. Now, if we continue, are there any questions so far? All right, just kind of reviewing here. Now, here, if you have a 20-pound weight lifted 6 feet off the ground, and actually let me unhighlight, hold on here, let me just highlight this for the moment. Whoops, that didn't work. Remove, highlight. Thank you. Okay. So if you're going to lift a 20-pound weight 6 feet off the ground, well, it's easy to compute the work. Work is 20 pounds, times a distance of 6 feet. So that's 120 foot-pounds. Now, these equations, I mean, these little examples that we did, okay, where, again, you're using work equals force times distance. These examples are where the force is a constant force. And that's something probably you've seen these kind of problems most likely in your science classes, maybe in high school, okay? But now we're going to be a little more sophisticated, so to speak. What if the force is not constant? What if the force were to change? Okay, what if the force were to change with respect to x? Well, that's what they're talking about now down here. Okay, so let's suppose, I'm going to highlight this right here. Because every word's critical, really. Now what we're going to do is suppose that an object moves along the x-axis in a positive direction from point x equals a to x equals b. Okay, and at each point a force acts on the object, but the force is a function of x, and f is a continuous function. How could we compute the work in moving the object from A to B when the force varies with x? Well, we can take the interval from A to B and divide it up into subintervals, which we always are doing in these problems, right? To get to the Riemann sum. We take the interval, we divide that interval up into subintervals. Okay, the force at each, and then for every subinterval, we can pick a point in the subinterval. So the force at each point is f of x sub I. Okay, now if n is large and delta x is small, if we pick our subinterval small enough, the force is going to be nearly constant over each subinterval. So for instance, the ith subinterval, if you wanted to know the work done in moving the particle from x sub I minus 1 to x sub I, okay, that's the ith subinterval, the work would be approximately equal to the force at x sub I times delta x. Okay, because delta x is the distance, right? Delta x is the distance of the ith subinterval. Every subinterval has the same distance delta x. So you're moving, I mean, it's like, hold on here. Let me just show the whiteboard real quick. Okay, so here's x sub I minus 1. Here's x sub I. Okay, you pick some xi star, say, in the interval. The interval has width delta x, and you're trying to see the work needed to move whatever you're moving across, like this distance. I put it in red. Okay. Well, if the force, and of course the force you're applying is a function of x. So if this delta x is real small, then the force across the entire subinterval is basically a constant. Okay, I mean, it's not constant, but it's very close to being a constant. Okay, so the you can take your force, okay, and multiply. I mean, again, this is the force here, right? Take your force times delta x, and that's going to equal the work that was done on the ith subinterval. And if you wanted the total work, okay, you would just add up all the pieces of work along your interval from A to B. In other words, this would be how you would approximate the work. Are there any questions so far? See, we need calculus to be able to handle the situation when the force varies with x. If the force is constant, it's no problem. But when the force is a function of x, which is more realistic, you need calculus to analyze it. Now, what do you think we're going to do with this Riemann sum? I mean, this is an approximation, what you're seeing in this Formula 3. To find the exact amount of work, what are we going to let n go to?
Infinity.
Infinity. That's right, Maria. That's right, Leping. So it's like you're taking your interval from A to B and you're breaking it up into tinier and tinier subintervals. So the number n of subintervals increases. And in the limit, this work is going to become the integral of the force being applied dx with respect with limits a and b. Okay, are there any questions on that? Okay, well then let's move on here. Let's look at an example here. And I actually, though, want to go to the second example here. Well, it's going to relate to Hooke's law. Okay, how many have heard of Hooke's law? Okay, Maria has. So Hooke's, and Jacob has. So Hooke's law has to do with, well, what it does is, Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is equal to k times x. Okay, so you see there in figure 1, you have a let's see here. Well, you have a spring, okay, and there's an object attached to it, and it's in like neutral position, okay, and they're assuming there's no friction on the surface because that'll make that if there's what's called damping, that makes things more complicated. But we handle that kind of situation in differential equations, Math 282. Okay, but for now we're dealing with a frictionless surface. So notice then in picture B, how far is the spring stretched from its natural position? How far, based on the picture?
X.
That's right. That's right. It is moved a distance of x, and the force f of x is equal to k times x. So how many have noticed when you stretch a spring, the more you try to stretch it, the harder it is to stretch. How many have noticed that? Like maybe a slinky or I mean, I'm sure we've all taken a spring and tried to stretch it, even as kids, right? But how many of you have done that? Taken a spring and try to stretch it? Okay, Jacob has, and okay, tall, and do you notice it gets hard? Does it get harder the more you try to stretch the spring? The harder it gets to stretch it. How many have noticed that? Tal has, okay, and Jacob has, and that's because of Hooke's law. Because the force, you're fighting the force of the spring. The force you need to apply has to counteract the force of the spring. And the force equals K times X. So the force is proportional to the distance X that you're trying to pull that spring from the neutral position. Okay, so, but this is an example now. This is an example, Hooke's law. Hold on here, this is an example of a force that varies with X. So we need calculus to help us compute work needed to stretch a spring with Hooke's law. So let's look at example 2. Absolutely amazing. Okay. And I guess I highlighted some things here. I'll let it highlighted on this one. So in this example, they say a force of 40 newtons. This is example 2 from section 6.6. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Okay, well, let's talk about that. So according to Hooke's law, the force required to hold the spring stretched X meters beyond its natural length is F of X equals K times X. Well, when the spring is stretched from 10 centimeters to 15 centimeters, okay, it's stretched from, so the spring, if natural length of the spring is 10 centimeters, you're stretching it to a length of 15 centimeters. So you've stretched it 5 centimeters. But remember, and maybe what I'll do kind of to, let me just, I'd like things to be a little dynamic here. So what you're doing, though, is you have to, of course, convert that 5 centimeters to 0.05 meters, right? How many centimeters are in a meter?
100.
100, okay. So, okay, good, Maria. So now, that's fine. Whoops, hold on, now where's my thing? All right, let me get this off. Okay, so that means then that F of 0.05 is equal to 40. You see, what we need to find is the spring constant. So we're using information in the problem to find the spring constant. So now, let me hold on. Let me unhighlight this. Please let me know if you have any questions, okay? So now 0.05 times K is equal to 40, okay? Because the function is equal to K times X. Okay, well, K times 0.05 equals 40, so K is 800. Now we've determined the spring constant, and so now we're able to find the work done in stretching the spring from 15 centimeters to 18 centimeters. Okay, and on that note then, oh wait, question? Yes, Nathan?
Where did 40 come from?
Oh, in the problem, in example 2, right in the beginning there, it says a force of 40 newtons is required.
Oh, I got
so, okay, no problem. Good question. Okay, well, so now let me just remove this. Now we uniquely know what the force is, okay, for this spring, and it's 800 times X, and so the work needed to stretch the spring from 15 centimeters to 18 centimeters would be equal to the integral from 0.05 to 0.08 of 800x dx. And that'll turn out to be 1.56 joules. Okay, are there any questions on that? Leping?
Professor, why the integral is from 0.05 to 0.08?
Okay, why is it from 0.05 to 0.08?
Uh-huh.
Well, in the problem here, hold on, let me go back up. They're asking here, I'll put it in pink, how much work is done in stretching the spring from 15 centimeters to 18 centimeters? So 15 centimeters is 5 centimeters beyond the natural length of the spring, because the natural length of the spring, it says there in the first paragraph, it says it's 10 centimeters. And 18 centimeters is 8 centimeters beyond the natural length of the spring. So 5 centimeters to 8 centimeters is equivalent to 0.05 meters to 0.08 meters. Okay, all right, very good, very good. Here we are. Okay. Are there any questions? Okay. Well, the next example I want to talk to you about deals with work needed to lift a cable. But I want to go to the example that I have here. I'm going to do my own little example here. Let's see. Let me bring it up. Okay, let me give you a moment to copy this example down. Okay. Let me give you a moment to do that. Okay, give you a little more time here. Okay, so this problem, we have a 1,600-pound elevator suspended by a 200-foot cable that weighs 10 pounds per feet. How much work is required to raise the elevator from the basement of the building to the third floor, a distance of 30 feet? Okay, and incidentally, of course, we all heard this, this problem, since they mentioned building, I'm sure we've all heard the sad news today about I think it was in Florida, the collapse of the apartment building, the one part of it. How many have heard this in the news? Okay, Maria has, and Samuel, and Leping, and Rayon, and this just, it just shows you. I mean, I hope we all hope they find survivors, but it does show you how important math. I mean, we don't know really the root of the problem. We don't know what the problem was. But what you're learning here, physics and engineering, is involved in building buildings, right? And so what you're learning is really important stuff. And of course, we don't know what happened. They'll let us know. But I'm just saying, this material you're learning, engineers, when they apply their knowledge and design things, it really affects lives. So okay, so it affects lives in that, when, like, I've heard, well, if engineers do a good job, then things are safe. And if mistakes are made, then things could not be safe. Of course, but we don't know what happened here in Florida. But all right. So let me ask you, how should we start this problem? What do you think might be helpful to start this kind of problem? Well, let me ask you this. What units would work be in for this problem? I mean, we're going to find work. What would the units be for the work? Would it be joules? Would work be in joules for this problem? Or would work be in
Foot-pounds.
Foot-pounds? That's right. That's right. Here's a big giveaway. 10 pounds per feet. Pounds. Feet. Okay. All right. Now, incidentally, if they gave measurements in inches, what would you do to the inches?
Convert them to meters,
Well, how about convert them to,
centimeters?
instead of, how about feet? Because you see, if it were we're dealing in foot pounds. So if we were in inches, we would be converting them to feet. But Michelle, if in another problem we had like centimeters, we would then convert the centimeters to meters. So you're on the right track. Okay, so let's look at this problem here. A very applied problem. Now I'm going to give you a chance to copy some things down. First of all, I'm going to give you a chance to copy this picture down. Okay, so what I've done is I've drawn a picture where, you know, here's the elevator down here, and here, this up here is the top of the building. Top of the building, right? And the rope, okay, the cable is here. There's the cable. And what I'm doing is, well, let me let you copy the picture down, and then I'll talk about it a little more. Okay, so look in the picture, notice what I've done here. Okay, notice what I've done. I have two pieces of cable. Two pieces of cable, okay, that I've just shown here. I mean, I can take the entire red cable and break it up into a bunch of little pieces of cable. Okay. Now, let me just see here one moment. I want to kind of keep things nice and neat here. So let's call this piece of cable the first, let's just call that, no, I have a better idea. Hold on. Yeah, I'll call it the, well, Roman numeral 1, okay? Roman numeral 1 piece of cable. And here we have Roman numeral 2 piece of cable. So Roman numeral 2 and Roman numeral 1. Maybe I can make that a little bit, just a little bit neater here. Hold on. I don't want to go too, just got to be real careful here, you know. Hold on. little neater. So if you were to consider Roman numeral 1 piece of cable, and then consider Roman numeral number 2 piece of cable, which piece of cable is going to take more work to bring up to the building? Because you see, in order to raise the elevator, well, no, I'm not saying this the right way. Hold on, I didn't mean bring up to the building, but hold on here. I mean, do you agree that for the elevator to move, the cable that holds the elevator, that red cable, has to move? All right, are we all in agreement with that? Abadar agrees. Okay, so in other words, to compute the work, we don't not only have to find the work needed to move the elevator, but we need to find the work needed to move the cable that holds the elevator, okay, to the top of the building. So the first piece of cable here, this or cable Roman numeral number 1, that piece of cable is x1 feet from the top of the building. Cable Roman number 2, Roman numeral number, I'm sorry, scratch that. I'm sorry. The first piece of cable here is x2 feet from the top of the building. The second piece of cable here, Roman numeral number 2, is x1 feet from the top of the building. Okay, so which piece of cable, well, I want to say this the right way. I want to make sure I'm saying this the right way. I got to be very careful how I say this. I got to be very careful how I say this. Let me phrase this another way. This is not exactly how I want to phrase this. The picture's fine. Let me go to the whiteboard for a moment. Okay, hold on here. Let me draw the cable. Here's the top of the building here. Okay. Now, here's the elevator down here. This is the elevator. And I'm going to highlight maybe in this color here. Well, no, let's do this color. I'm going to call this 30 feet. 30 feet of cable. Let's make it a little more. I got to kind of to show what I want to show here. There's 30 feet of cable, okay? Obviously, picture not drawn to scale. When the elevator moves up 30 feet, okay, when the elevator goes from the basement to the 3rd floor, a distance of 30 feet, does this 30 feet of cable get moved to the top of the building? This top 30 feet of cable? Does it get moved
Yes.
to the top of the building? Yeah, it has to, right? It's on a winch. The cable's on a winch or something at the top, and the winch moves. So in order to move the elevator up, the cable has to move. the top 30 feet of cable moves to the top of the building. Okay. Leaving you, by the way, with how much cable just still that hanging there, that has not moved to the top of the building. In other words, what would this, how many feet of cable would this have to be?
170.
That's right. That's right, Nathan. 170 feet of cable. And this 170 feet of cable, this just gets moved blank blank. The 170 feet of cable, okay, and it's the cable at the bottom, we could call it, but that 170 feet of cable just gets moved how many feet?
30.
I'm sorry, LePain?
30.
30 feet, that's right. So you got two things that when this elevator goes up 30 feet, you have the elevator itself moving 30 feet, and then you have the 170 feet of cable moving 30 feet. Okay, so the work to move the elevator 30 feet would just be what? What would the work be? I'll call it work sub 3 for the elevator. What's the work that's going to be needed to move the elevator? It's something times something. Well, the elevator moves 30 feet. And how heavy is the elevator?
1,600 pounds.
That's right. So, and that's there's no, I mean, that's like a constant weight just being lifted 30 feet. So are we okay on that? There are 3 portions in computing this work. 3 portions, okay? First is the elevator. Now, what about the cable? What about the 170 feet of cable? What would the work be there in moving that cable? Cable gets moved 30 feet, and we multiply that by how much weight?
$2,000.
Well, how much does the cable weigh? How much does the cable weigh per foot?
10.
10 pounds per foot. And how many feet are there to move?
200.
How many? I'm sorry?
I mean, you're moving all 200 feet, right?
You are, but the 200 feet of cable, we have to treat the top 30 feet of cable differently than the bottom 30 feet of cable. Because I'm sorry, we have to treat the top 30 feet of cable different than the bottom 170 feet of cable. Because the bottom 170 feet of cable just gets moved 30 feet. The top 30 feet of cable actually gets moved to the top of the building. So it works differently. It works differently. The bottom 170 feet of cable is just like dead weight that gets moved 30 feet. That bottom 170 feet of cable never reaches the top of the building. So it's just like the elevator. So we got to take for the bottom 170 feet of cable, to compute the work, well, work is force times distance. The distance is 30 feet. What's the weight for 170 feet of cable? The cable weighs 10 pounds per foot, and we have 170 feet, so it would be, sorry?
1,700.
That's right, 1,700 pounds. Okay? So now what we have to do is worry about the top 30 feet of cable. One moment. Okay, just picked up the phone and hung it up there. All right, so here's the thing. The top 30 feet of cable is the part where we need the calculus. Because let's look at two pieces of cable. Let's look at two pieces of cable here. Okay, here's this piece of cable, cable piece 1, and here's cable piece 2. Do both cable piece 1 and cable piece 2, do they get moved to the top of the building? And they're each of width delta x, by the way.
Yes.
It does. Now, that's right. Which piece 1 or piece 2 of cable, does it take more work to get to the top of the building? See, what we're doing is we're taking the top 30 feet of cable and we're breaking it up into a bunch of little pieces of cable. The first piece of cable needs to go this far. Okay, the second piece of cable needs to go this far. So which piece of cable, cable 1 or 2, does it take more work to bring that piece of cable to the top? That's right, Arbidar, piece 1. And why is that?
It goes a long distance.
That's right, Leping. It's a further distance. So you see, what happens is for the top 30 feet of cable, we can't treat the top 30 feet of cable like the bottom 170 feet of cable, because the force needed to bring we take the top 30 feet of cable and we can, in other words, what I'm trying to say is the top 30 feet of cable, bringing the top 30 feet of cable to getting it to the top of the building would require the same amount of work as if we took that top 30 feet of cable, broke it up into little equal pieces, and brought each piece separately up to the top of the building. You see what I'm saying? If the work needed to bring the top 30 feet of cable to the top of the building would be equivalent to taking the top 30 feet of cable and breaking that top 30 feet of cable up into a bunch of little pieces, each of same width, and then bringing each of them to the top of the building. Okay, that's so the work for like piece 1 of the top 30 feet of cable to bring to the top of the building differs from the work for the second piece of cable there. And so the work is a function of the distance from the top of the building that piece of cable is. And this is now where you need the calculus to help you. So let me go back to the page here. Are there any questions? I'm going to show you now the math, but are there any questions at all?
So you're saying that the top requires more work than the bottom half?
Well, it doesn't require, I'm not saying it actually requires less work, because once the top 30 feet of cable, first of all, it's less cable than the bottom 170 feet of cable, less to lift, but also the top 30 feet of cable, once once a piece of cable gets to the top, there's no more work to be done. You see? Once a piece of cable reaches the top of the building, there's no more work to be done. So like a very good question, Marcus. Let me go to the thing here. Hold on one moment. let me just hold on here. Let me go back to the thing and let me go to the second page now, or the page of the solution, and talk about this. So the total work consists of 3 components. Okay, this component here is the work for the elevator. Elevator weighs 1,600 pounds. We're moving at 30 feet. Okay, that's the work for the elevator. The work for the bottom 170 feet of cable, okay, is just 170 feet times 10 pounds per foot, which gives us that 1,700 pounds, because the feet simplify out, and you're left with foot pounds. So you notice that I'm carrying my units here in my math, so that I can make sure that my units are right. How many recall doing that in chemistry? That kind of unit analysis, how it's helpful. Okay, Renard remembers that, and a number of you, other of you do too. So, but now here's well, this is the more difficult part, the top 30 feet of cable. So the top 30 feet of cable, the weight of the ith piece of cable, and the ith piece of cable, and you can see from the picture here, the ith piece of cable has a width of delta x. Okay, so delta x feet is the length of the ith piece of cable, and that piece of cable weighs 10 pounds per foot, but you're moving it xi feet. Okay, and the xi feet is going to vary from what's going to be the limits on the xi feet, because we know this is going to turn into an integral. What do you think the limits are going to be for the integral for this first part of the work? Marcus? Yeah,
Would it be 200 and 0?
Well, the 0 is good, but let me ask you this: the top 30 feet of cable, that top 30 feet of cable, the piece that's 30 feet down, how far does that get moved? You're moving the elevator 30 feet. So the top 30 feet of cable, okay, the piece of cable at the very top is right there, right? That's 0 feet, it gets moved. But then 30 feet down, that piece of cable located at 30 feet down from the top of the building, how far does that piece of cable get moved? What do you think?
30 feet?
30 feet, you got it. You got it. So, of course, we're going to take the limit as n goes to infinity, this Riemann sum here, we're going to let n go to infinity. Okay, in other words, that top 30 feet of cable, we can break it mathematically into smaller and smaller pieces, each one getting moved to the top of the building, and the force needed to bring that to the top of the building is almost constant for each piece, but it differs from piece to piece, right? Or the work differs from piece to piece because the distance is different. Notice this first term only applies to the top 30 feet of cable. So now if you're ready, I'll go to the next page and we'll get to the final answer. Are we ready to go to the next page? Okay. Good, good. Okay, does anybody need more time to copy? All right, well, this Riemann sum is going to turn into an integral. Okay, Jazzy. Okay. Let me know if you have any questions. Okay, good. Very good. So here we go. The integral, well, I mean, let me just go back here. This limit here, right, is going to turn into an integral. Okay, and what's the delta x become in the integral? What's the delta x become?
0.
Well, it becomes a dx, right? The limits are from 0 to 30. So we've accounted for delta x. Okay. The units are in foot-pounds. Okay. What's left? What's left here? 10 and xi. That's going to become 10x when you take the limit of that Riemann sum. And so here we go. Renaud, the 5100 came from, let me just show Renaud that real quick, fast, class. Here, Renaud, the 170 times 10 times 30. Let me just see one thing. I think I might, let me just check. Do I have an error here? Hold on. No, yeah, that's good. 170 times 10 times 30 is 51,000. That's where that came from. Okay, good, good. And then you're welcome. And then the 48,000 here, the 48,000, okay, that comes from the 1,600 pounds that the elevator weighs times 30 feet. That's 48,000. So when you work this out, you're going to get 103,500 foot-pounds. And that's the work needed. Okay, are there any questions on that? Okay, I'll stop the recording.